Are we alone? The desire to know our place in the universe is a core human yearning, and people have pondered the question for thousands of years. Indeed, hundreds of years before the birth of Christ, Greek philosophers such as Anaximander and Epicurus speculated that the cosmos is teeming with planets, many of which may support life. However, we couldn't move beyond mere speculation for a very long time until we invented telescopes and developed a proper understanding of the scientific method. Humanity notched both of those milestones centuries ago, and scientists are now going great guns in the search for alien life. Well, going great guns is a bit of an overstatement, but we've made considerable progress, especially in recent times with groundbreaking discoveries made by James Webb. Thanks to the James Webb Space Telescope, we have just got one more step closer to discovering the signs of our cosmic neighbors on exoplanets many millions of miles away from home. Join us as we dig deep into how the James Webb Space Telescope is hunting down alien worlds. The James Webb Space Telescope, the most powerful telescope ever built, has gathered some extraordinary images since it was launched by NASA just over a year ago. There have been shots of stars on the cusp of death, of stars violently colliding together, and even of ancient galaxies that have challenged our very understanding of the cosmos. But for many, it's the study of exoplanets, planets outside our solar system, that really justifies the telescope's $10 billion price tag. Since its launch, a team of 120 international astronomers working on the James Webb Telescope, gathering images of exoplanets. Roughly speaking, there are 4 types: gas giants like Jupiter and Saturn, Neptunians, which typically have hydrogen and helium-dominated atmospheres with cores of rock and heavier metals, super-Earths, bigger than our planet, and terrestrials, which are compact with rocky surfaces like Mercury, Venus, Earth, and Mars. The vast majority orbit a star, though there are sunless rogue exoplanets that roam the galaxy in perpetual darkness. Over the past decade or so, we've begun to understand just how widespread these planets are, including those resembling our world, known as exo-Earths. The first exoplanet, a Jupiter-like planet, was not confirmed until the early 1990s. Then, with the launch of the Kepler space mission in 2009, we began discovering a startling array of various solar systems with exotic planets orbiting their stars. To date, we have spotted 5,332 confirmed exoplanets, orbiting in some 3,131 planetary systems. But this isn't even the tip of the iceberg. For perspective, there are around 100 billion stars in our Milky Way. Since we now know from various space missions that most stars host planets, this begins to give you an indication of just how many exoplanets could exist in our galaxy. And then, beyond our galaxy, there are estimated to be 200 billion galaxies in the universe, each containing potentially hundreds of billions of stars with their own exoplanets. In the landmark 1980 television series Cosmos, the astronomer Carl Sagan provocatively posed the question, are there a greater number of planets in the universe than grains of sand on all the beaches on Earth? Almost half a century later, various space missions, including the James Webb Telescope, have given the answer. There are more planets than grains of sand, and not by a little, but by a lot. As Sagan said, we live on an insignificant planet of a humdrum star lost in a galaxy tucked away in some forgotten corner of a universe in which there are far more galaxies than people. However, the difference today is that we know the universe is far bigger than was thought back then, which raises the question, are we alone in the universe? The obvious conclusion from all this is that the likelihood of life existing in some form in the universe is quite high. Already, many of the exoplanets we've observed are inhabitable zones, known as the Goldilocks zones. This means that they orbit their stars at a distance that is not too hot or not too cold, a location that is ideal for liquid water to exist for most of a planet's lifetime, which is one of the first necessary criteria for life to form. Terrestrial planets, like our own, are prime candidates for hosting life, as they are more likely to have hard surfaces and liquid water oceans. Oceans can have a profoundly stabilizing effect on the climates of these planets, giving nascent life forms the stability needed for evolution to happen. One of the best candidate planetary systems to search for signs of life on another planet is TRAPPIST-1. This is a system of 7 roughly Earth-sized planets in the constellation of Aquarius, closely orbiting a very dim and cool star, not much larger than Jupiter. According to Björn Benecke at the University of Montreal, 3 of the planets in TRAPPIST-1 orbit in the habitable zone of their host star. Efforts are already underway to target these 3 planets with the James Webb Telescope to search for what scientists call biosignatures. Now, to be clear, the detection of life on another planet will not necessarily mean an alien civilization exists on another planet, nor that we are about to have some form of communication with such life forms. The evidence of the discovery of life will probably be found by observing imbalances in ratios of chemical species, ozone and carbon dioxide, for example, which would not otherwise naturally exist without possibly some form of biological activity driving this disequilibrium. In a recent observation, the powerful space telescope studied 4 flares erupting from the star TRAPPIST-1, a cool red dwarf that's located about 41 light-years from Earth in the constellation Leo. Researchers decrypted the flare's radiation from the star's regular light, something that could aid the hunt for habitable conditions in this extraordinary system. As research lead author Ward Howard, a NASA Sagan Fellow at the University of Colorado Boulder, said in a statement, "Because of the James Webb Space Telescope, it is the first time in history that we've been able to look for planets around, other stars that have the sorts of secondary atmospheres you could find around, say Earth, Venus, or Mars. If we want to learn more about exoplanets, it's really important to understand their stars. Red dwarfs like the Jupiter-sized TRAPPIST-1, which has a mass around 9% that of the Sun, are the most common stars in the Milky Way and, despite their small stature, are also the most active. TRAPPIST-1 emits powerful blasts of energy as flares several times a day. Our own Sun, by contrast, erupts with similar outbursts just once a month or so. The violent activity of red dwarfs makes studying the atmospheres of their exoplanets a challenge. Astronomers study alien atmospheres by observing light as it passes through them, and chaotic emissions of stellar radiation complicate this process. Howard and his colleagues addressed this challenge by observing flares emerging from TRAPPIST-1 over a period of roughly 27 hours. They then separated these bursts of light from the regular light coming from the star, filtering out around 80% of the flare-based radiation. If you don't account for flares, you could detect molecules in the atmosphere that aren't really there or get the amount of material in the atmosphere wrong, Howard explained. Additionally, not only was the team able to observe a stellar flare in certain wavelengths of infrared light for the first time with James Webb, but they also captured the evolution of those 4 flares in detail, watching over several hours as they grew in brightness before peaking and becoming dim again. The researchers said that this method could be key for obtaining clearer images of planetary atmospheres and will likely be applied to the TRAPPIST-1 system in particular. Further into space, NASA's James Webb Space Telescope has also spotted an early yet tantalizing piece of evidence that an exoplanet could be covered in a massive ocean that's possibly harboring life. The planet dubbed K218b after its host star K218, which is located about 120 light-years from us. That's not terribly far in space terms, but we won't be popping over there for an in-person visit anytime soon. K218b orbits in the habitable zone of its star, a region where liquid water could be present on the planet. The exoplanet may be what's known as a Hycean world, one that is covered in water with a hydrogen-rich atmosphere. The name is a combination of hydrogen and ocean. Astronomers from the University of Cambridge identified Hycean planets as a new class of habitable planet in 2021. The researchers encouraged investigating these worlds for biosignatures, evidence of life, as we continue our search for life beyond Earth. According to University of Cambridge astronomer Niku Madhusudan, lead author of a paper on the Webb results, traditionally, the search for life on exoplanets has focused primarily on smaller rocky planets, but the larger Hycean worlds are significantly more conducive to atmospheric observations. This is where Webb's powerful instruments come in. Webb is building off observations made by the venerable Hubble Space Telescope. Hubble already discovered water vapor in the atmosphere of K2-18b. Webb has now detected carbon-bearing molecules methane and carbon dioxide in K2-18b's atmosphere. NASA say the detection of those molecules combined with a shortage of ammonia supports the idea. The planet is hiding an ocean under its atmosphere. Methane and carbon dioxide aren't the only molecules worth getting excited about. The telescope may also have detected dimethyl sulfide. According to NASA, on Earth, this is only produced by life. The bulk of the dimethyl sulfide in Earth's atmosphere is emitted from phytoplankton in marine environments. K2-18b is 8.6 times as massive as Earth, but it's less massive than Neptune. We have nothing quite like it in our own solar system. This lack of equivalent nearby planets means that these sub-Neptunes are poorly understood, and the nature of their atmospheres is a matter of active debate among astronomers, said NASA. Webb's data so far is a reason for excitement about K2-18b and its potential to host life, but it's too soon to celebrate. NASA cautions that an ocean on a planet like this might be too hot to be habitable. But should we be excited about Webb's results? Absolutely yes. They beautifully demonstrate how far we have come in the hunt for life game. They also revealed evidence for a whole new class of habitable planet, and they showed what finding a biosignature in the future could look like. In short, the game, as Sherlock Holmes once said, is afoot. What's interesting, the Premier telescope has already made some stunning discoveries about exoplanets near Earth. The telescope spotted water on the Neptune-size exoplanet GJ1214b, which is around 40 light-years from Earth, and found that TRAPPIST-1b, the second closest exoplanet to the star in the TRAPPIST-1 system, likely has no atmosphere at all due to its extreme heat. The spacecraft also glimpsed a gigantic dust storm in the atmosphere of VHS1256b, a super-Jupiter exoplanet, 40 light-years from Earth. Closer to home, the world's supreme space observatory also has made a groundbreaking discovery on Jupiter's moon, Europa. Its infrared camera captured images of this moon's unique terrain, revealing intriguing traces of life in the form of abundant carbon dioxide. Jupiter's moon, Europa, is one of a handful of worlds in our solar system that could potentially harbor conditions suitable for life. Previous research has shown that beneath its water ice crust lies a salty ocean of liquid water with a rocky seafloor. However, planetary scientists had not confirmed if that ocean contained the chemicals needed for life, particularly carbon. Astronomers using data from NASA's James Webb Space Telescope have identified carbon dioxide in a specific region on the icy surface of Europa. Analysis indicates that this carbon likely originated in the subsurface ocean and was not delivered by meteorites or other external sources. Moreover, it was deposited on a geologically recent timescale. This discovery has important implications for the potential habitability of Europa's ocean. According to Geronimo Villanueva of NASA's Goddard Space Flight Center in Greenbelt, Maryland, lead author of one of two independent papers describing the findings, on Earth, life likes chemical diversity. The more diversity, the better. We're carbon-based life. Understanding the chemistry of Europa's ocean will help us determine whether it's hostile to life as we know it, or if it might be a good place for life. We now think that we have observational evidence that the carbon we see on Europa's surface came from the ocean. That's not a trivial thing. Carbon is a biologically essential element, added Samantha Trumbo of Cornell University in Ithaca, New York, lead author of the second paper analyzing these data. Webb finds that on Europa's surface, carbon dioxide is most abundant in a region called Terra Regio, a geologically young area of generally resurfaced terrain known as Chau's terrain. The surface ice has been disrupted, and there likely has been an exchange of material between the subsurface ocean and the icy surface. As Trumbo explained, previous observations from the Hubble Space Telescope show evidence for ocean-derived salt in Terra Regio. Now we're seeing that carbon dioxide is heavily concentrated there as well. We think this implies that the carbon probably has its ultimate origin in the internal ocean. Scientists are debating how much Europa's ocean connects to its surface. I think that question has been a big driver of Europa exploration, said Villanueva. This suggests that we may be able to learn some basic things about the ocean's composition even before we drill through the ice to get the full picture. Both teams identified the carbon dioxide using data from the integral field unit of Webb's near-infrared spectrograph. This instrument mode provides spectra with a resolution of 200x 200 miles or 320x 320 kilometers on the surface of Europa, which has a diameter of 1,144 miles, allowing astronomers to determine where specific chemicals are located. Carbon dioxide isn't stable on Europa's surface. Therefore, the scientists say it's likely that it was supplied on a geologically recent timescale, a conclusion bolstered by its concentration in a region of young terrain. According to Heidi Hamel of the Association of Universities for Research in Astronomy, a Webb interdisciplinary scientist leading Webb's Cycle 1. Guaranteed time observations of the solar system. These observations only took a few minutes of the observatory's time. Even with this short period of time, we were able to do really big science. This work gives a first hint of all the amazing solar system science we'll be able to do with Webb. Villanueva's team also looked for evidence of a plume of water vapor erupting from Europa's surface. Researchers using NASA's Hubble Space Telescope reported tentative detections of plumes in 2013, 2016, and 2017. However, finding definitive proof has been difficult. The new Webb data shows no evidence of plume activity, which allowed Villanueva's team to set a strict upper limit on the rate of material potentially being ejected. The team stressed, however, that their non-detection does not rule out a plume. There is always a possibility that these plumes are variable and that you can only see them at certain times. All we can say with 100% confidence is that we did not detect a plume at Europae when we made these observations with Webb, said Hamel. These findings may help inform NASA's Europa Clipper mission, as well as European Space Agency's upcoming Jupiter Icy Moons Explorer. And further out into the cosmos, for the first time, the Webb telescope has glimpsed potentially life-giving carbon compounds in an infant star system more than 1,000 light-years from Earth. Known as methylcation, the molecule is important because it aids the formation of more complex carbon-based molecules. Methylcation was detected in a young star system with a protoplanetary disk known as D203506, which is located about 1,150 light-years away in the Orion Nebula. Carbon compounds form the foundations of all known life, and as such are particularly interesting to scientists working to understand both how life developed on Earth and how it could potentially develop elsewhere in our universe. The study of interstellar organic chemistry, which Webb is opening in new ways, is an area of keen fascination to many astronomers. The unique capabilities of Webb made it an ideal observatory to search for this crucial molecule. Webb's exquisite spatial and spectral resolution, as well as its sensitivity, all contributed to the team's success. In particular, Webb's detection of a series of key emission lines from methylcation cemented the discovery. As Marie-Aline Martin-Drumel of the University of Paris-Saclay in France, a member of the science team, said, "This detection not only validates the incredible sensitivity of Webb, but also confirms the postulated central importance of methylcation in interstellar chemistry." While the star in D2 03506 is a small red dwarf, the system is bombarded by strong ultraviolet or UV light from nearby hot, young, massive stars. Scientists believe that most planet-forming disks go through a period of such intense UV radiation, since stars tend to form in groups that often include massive UV-producing stars. Typically, UV radiation is expected to destroy complex organic molecules, in which case the discovery of methylcation might seem to be a surprise. However, the team predicts that UV radiation might actually provide the necessary source of energy for methylcation to form in the first place. Once formed, it then promotes additional chemical reactions to build more complex carbon molecules. Broadly, the team notes that the molecules they see in D2 03506 are quite different from typical protoplanetary disks. In particular, they could not detect any signs of water. This clearly shows that ultraviolet radiation can completely change the chemistry of a protoplanetary disk. It might actually play a critical role in the early chemical stages of the origins of life. Elaborated Olivier Bernet of the French National Center for Scientific Research in Toulouse, lead author of the study. After all, James Webb's results show we're on a path to finding alien life. Most likely, within the next few decades, we may well have hard evidence for the existence of alien life on worlds light years distant from Earth. And this is a good sign for NASA. 2 years ago, the National Academy of Sciences in the United States charged NASA with the task of developing a space mission to search for biosignatures on exoplanets by the 2040s. However, having said that, even with all the technical achievements showcased by the James Webb Telescope and other exoplanet missions launched by NASA, this will be incredibly hard work. Studying and characterizing exoplanets is not a straightforward task, hence why we have only identified several thousand when we know there must be trillions. So far, the vast majority of exoplanets discovered have not been detected directly. We have determined their presence either by observing a shadow they've cast while passing in front of their host star, or by seeing a subtle wobble they have induced on such a star. The issue with trying to take images of an exoplanet is the difficulty in overcoming the incredibly bright glare given off by the planet's host star, which is vastly brighter than the planet closely orbiting around it. For the past 20 years, astronomers have been working on trying to develop instruments and software that will give telescopes the ability to discern the faint light of an exoplanet from that of its host star. To get a sense of the challenge that astronomers face, imagine sitting in London trying to take a picture of a firefly fluttering around a searchlight that is pointing directly at you. Now try doing the same task, but with the firefly and searchlight placed in Bristol. Efforts like this have already returned direct images of a handful of exoplanets. Not exo-Earths yet, but massive super-Jupiters. Even if we need to wait a couple of decades for a future space telescope to detect biosignatures on an exoplanet, the James Webb Telescope will bring us closer than ever before to achieving this goal. It might also be able to tell us something about the birth story of exoplanets and thus help to place our own origins in context. After all, if we know how our planet came into being, it could reshape our entire thinking about the cosmos and our place in it. Understanding precisely what combination of elements planets are made of might tell us something about where in the vicinity of their stars they formed. For example, A planet which formed by gradually gobbling up material in its circumstellar disk as it orbited its host star will have a very different makeup than a planet that formed more like its host star via the collapse of an interstellar cloud. Astrophysicists will be able to trace these chemical fingerprints into a coherent narrative of how planets are born and evolve. 3 decades ago, we hadn't yet found an exoplanet. We now know of thousands. We know, too, that the sheer number of these planets waiting to be identified is hardly even comprehensible. Written numerically, it would be 1 followed by 22 zeros. For perspective, a billion is 9 zeros. In other words, with so many planets lurking around our universe, it won't be much longer until we discover we aren't out here all alone. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.